So I think we left off talking about model calibration. So the next slide is scenarios. You've now got a model set up, you've calibrated your model to known conditions, and it's time to start running some simulations. So what are we going to simulate? Most likely a number of scenarios, probably not just one. Actually, and by the way, I'll just mention that a lot of the stuff we're talking about here will be things that you need to put in your model report. So the people who are responsible for preparing a model report should definitely kind of pay attention to some of these topics. One of the main things that you need to represent is time snapshots. So you can either simulate a long period over time, or you can look at individual time periods. The reason we might look at individual time periods is that it's really difficult, if not impossible, to simulate like a 200-year period or a 100-year period or whatever. And we need to look at what this project will do to the environment, not just today, not just while it's operating, but as far into the future as possible. So just about any type of project, really except those that are located within a city, are intended to be one day reclaimed back to nature. So if it's something inside a city, there's really not much expectation about reclamation, because we don't expect our cities to return to nature anytime soon, if ever. But anything that's out on the landscape, a mine, a logging operation, a pulp mill, whatever, something that's way out in the middle of nowhere, there's almost always an expectation that the proponent will have a closure plan, a reclamation plan, some way to return the land, the water, and everything back to the way it was before the proponent was there. So some of the relevant time snapshots, and this doesn't imply that a certain EA or an EIA will have all of these, but these are some sort of common ones that might be relevant to a project. So a pre-development past, we talked a lot about that in regards to Site C in the Peace Athabasca Delta. We can't go back and measure the past, so we might need to go simulate it. What did the Peace Athabasca Delta or the Peace River or some area look like long before humans came along and dammed up the river? Then we have existing conditions, which is usually what you're going to base your calibration on. It might also be the baseline that you use. And I think particularly people who did surface water regime, I think they used existing conditions as a baseline. And typically that's not the way to go, but sometimes it is done. So start of operations, no matter what type of operation it is, if it's big enough to have an EA, it's probably going to have some sort of a construction, land clearing, or other sort of big initial disturbance. And then worst case periods of operation. So the worst case periods of operation really applies to, in any given operation, there will be some period. It's very VC specific. So for example, if you're looking at air quality, you would look at that time period of operations when you expect to have the maximum emissions, or you might look at a project in terms of when will be the maximum emissions from this particular project plus all the projects around it, because that will lead to the worst air quality. For any sort of land disturbance, it's usually near the end of the operation when most of the disturbance has occurred. In some cases, there's progressive reclamation, in which case the worst case is not always near the end. But usually it's going to be towards the later end of the project when most of the types of disturbance are the greatest and nothing or very little has been reclaimed yet. And then regardless of whether or not this is the worst case, typically you need to look at the end of operations. So what does this project look like the moment before it shuts down? And then the reclamation period. I actually don't know if Site C EIA looked at the reclamation period. I know it's planned to last about 100 years, but typically a large project like that has a timeline during which it'll operate, and then there needs to be some plan to actually reclaim it. And I know there has been a lot of dams that have been taken down, and it's a massive undertaking. But like I say, I don't know what was done for Site C, but that would definitely be an interesting thing to look at if you're checking out their assessment. And then the walkaway. So the walkaway period is usually applicable to any sort of operation that needs to post a bond, and they need to get a reclamation certificate from the government in order to reclaim their bond. So they've paid maybe $100 million, which would cover the cost of a site cleanup if they don't clean it up themselves. When they do clean it up, the government issues a reclamation certificate, gives them back their bond, and they walk away. So walk away really means the landscape has been reclaimed. It doesn't mean it's completely back to natural conditions, but it means that it's on that trajectory and does not need any more active management. So for example, the forest might not be fully regrown on the plot, but trees are there and it's pretty certain that they will grow. There's no issues around toxicity, there's no issues around lack of substrate for things to grow. Basically, it's on that trajectory and it's pretty certain that it will return to a natural state. And then in a lot of cases, you need to look at far future. So what does it look like in sort of an undefined period, but far into the future once the landscape has regrown? Can it actually be returned to a natural state at some point in time? So those are the time snapshots. And then in addition to those, we have development scenarios. And now in a large EIA, what happens is we have these development scenarios, and for each development scenario, we do all of the time snapshots. And usually there's about five time snapshots from this list. So there's 2, 4, 6, 8. There's 8 listed there. Usually there's about 5, can be 4 or 6, whatever, but usually it's somewhere in that order. But now we do that same snapshot under 3 different development scenarios. So usually we do a base case, which is like a baseline, but not exactly. Essentially, it is, what does this landscape look like in the future and in the past without the project, so that we can then superimpose our project and we have a basis for comparison. So in the case of Site C, if they had done time snapshots, which they didn't really take this approach, they would look at what did it look like 60 years ago if the project wasn't built, although they would, in the base case, the other dams would still be there. What does it look like today without having the project, and what would the river look like 50 years from now if this project is not built? So now you're looking at usually existing projects, approved projects, basically really certain things that we know are going to be there with or without this project. And then the next development scenario is the project case or the application case. And in this one, we have the identical scenarios as the base case, but we superimpose our project into that. And that gives us a really clear basis for comparison so that we can actually assess changes from without the project to with the project. And then the third one is often very difficult to do. It's a cumulative effects case, also called the planned development scenario, has some other names, but essentially now we're looking at cumulative effects from all planned projects. And the word planned is kind of a loaded term. What does that mean? Does that mean anything that's on somebody's mind that one day might be built? Does it mean only things that have been submitted to the government? If we're looking 30 years into the future, it's really difficult to know what a planned development looks like. So typically what this means is any project where any other proponent has actually disclosed publicly that they plan to build something. So in other words, if you look at the area around Site C, you'll probably find that there are lots of fracking operations that might one day occur. There's a few mining operations that haven't been started, but on the website of the companies, they say we have plans to mine this area, and so that's a plan. And typically it's not actually up to the technical leads to do this. There will be somebody, usually a project manager, who is tasked with going out and finding every planned project on Earth that could possibly affect this study area, and they come up with something called the project inclusion list, and that's what you have to simulate in your model. Actually, a really good example is the Dunvegan Dam. Some people have probably come across that in what you've been reading. The Dunvegan Dam has been planned. It's just downstream of Site C, just across the Alberta border, south of the town of Peace River. It's been planned, it's gone through the EA process in Alberta, it was approved and then pulled, I think twice, and I believe there's a third attempt at it now. Somebody's proposed to build this dam, but that's a perfect example of a cumulative case or a planned development scenario. We know that people are intending to build this at some point. We can't exactly say when or who, and we don't know all the details, but we do know that that's a likely project in the future. And so then to do a cumulative effects case, we would take our project case where we've simulated the base case plus our project, and now we add anything else around it that is planned. And we do an effects assessment on that. And usually it's not quite as rigorous of an effects assessment because we've made a lot of assumptions, we've made a lot of kind of made things up because we don't have a good information base for all those other projects. It's very hypothetical, but we still need to look at that and say, okay, now given that there's all these other projects planned for the same area, is the project still a sustainable idea, or is this project essentially taking up all the capacity that nature has to be resilient, and one more project is now going to be a tipping point, and essentially that means that the project is taking up all the spare capacity, or however you want to call it, the assimilative capacity. It's essentially all nature can take before we are going to reach a tipping point if one more of these projects comes along. So that's usually something that would interfere with an approval or come with a lot of conditions and attachments. It's kind of hard to say how those are going to be assessed by the decision makers, in other words, the regulators. It's really variable in how they look at the cumulative effects case. But it definitely needs to be done in order to kind of ensure that this project is not going to be limiting for all other activities. Because if you think back to the definition of sustainable development, if I can remember the exact definition, it's the ability to use resources without compromising the future ability to use those resources, something like that. In other words, if you're now compromising the ability of other people to come and put a project here, it's not a sustainable development. Okay, so those are the very sort of standard ones. Now we have a bunch of what if scenarios, because all sorts of things can go wrong with a project, and the regulators want to know, and stakeholders want to know, that if something goes wrong, either it's not going to be that bad or the company has a plan to deal with it. So the big obvious ones are spills and malfunctions. So spills happen all the time. They can be anything from a gallon of gasoline being spilled at a fueling area to the Exxon Valdez and everything in between. So depending on what the project is, this can be a major part of it or sort of a minor part of it. So if it's for the minor part, it's kind of comes down to best management practices. Do we have a spill containment area? Are we following procedures? Are we doing all these things to make sure the spill doesn't happen? But for something large, like say a Kinder Morgan pipeline, a spill of that into a river could be fairly disastrous. So I haven't actually seen their EA, but I can assure you, I'm positive they would have looked at spills and malfunctions in a very rigorous way, because that's probably one of the biggest potential effects of that project. So they would have to do modeling, almost a full assessment on a bunch of hypothetical situations to understand what are the consequences if this happens, but more importantly, what can they do to avoid it or mitigate it? This often comes down to timing. So for example, if a pipeline spills into a river, how far downstream is the nearest water intake? Is there time to shut off the valves and warn people to shut off their intakes before the spill gets to them? And so this is very, very project specific. And sometimes it's done with modeling, sometimes not. Another one is market failure. So for pretty much any type of large project, it will be somewhat at the whim of the market. And so for Site C, you may or may not have come across this, but a huge pushback against Site C was the likelihood that BC does not actually need this electricity. And BC Hydro was often accused of building a project that BC doesn't need just so they can export electricity to the USA, which a lot of people were against. But say the electricity market crashes for some reason, somebody builds a nuclear power plant next door and now they're no longer importing the electricity and we actually don't need this project. Another one is mining with pretty much any type of mine. They're really subject to commodity prices. So you might hear about copper mines. Lots of copper mines in BC are sort of on again, off again. They'll shut down and go into care and maintenance if the price of copper goes below about $2 per pound. And that happens all the time. So mines shut down and then they come back and resume operations 2 years later when the price goes back up. And the reason that's important here is because if that price doesn't come back up, that mine is now a big open pit with nobody to actually fund the reclamation and nobody to actually fund continued development. And so what do we do there? So that's something you need to simulate. You often need to simulate something like that. It's not a strict requirement, but it's usually something the government will ask for, put in terms of reference. And then alternate development plans. This is similar to the alternatives assessment, but not exactly the same. With an alternate development plan, you might take this partway down the road of environmental assessment. You're not going to do a full assessment on each plan, but you might look at certain aspects of it, because this could help you develop a project in a more sustainable way or include better mitigation. But you're sort of modeling different scenarios of what could occur with the project to help understand better how you can control it and mitigate it and minimize harm. And then a whole separate category, which I'll get to on the next slide, is sensitivity scenarios. So in a sensitivity analysis, what we're doing is we're looking at a specific scenario that we've already simulated. Usually it's our project case with our worst case conditions. And now we're going to do a whole bunch of what if scenarios. And the what if scenarios don't even have to be realistic. It's really more about understanding the sensitivity of the environment or the sensitivity of the model to a certain occurrence. So for example, if we want to do a climate change scenario, we can't predict exactly what temperature the climate will change or the number of degrees the climate will change by in 40 years from now, because it relies on many, many variables that we have no control over. But we can say, okay, so if the planet warms by 4 degrees, here is what it means to our project. We often also don't know whether a region will become wetter or drier under climate change scenario, because that's also subject to a lot of different factors. Most of all, it is subject to political will to actually change emissions, which is impossible to predict. So we can't say in 50 years Kelowna will be 2 degrees warmer and 10% wetter. But what we can say is if Kelowna is 2 degrees warmer and 10% wetter, we can run that in a model and say this is the consequence. And we can run as many scenarios as we want, as long as we have good inputs and sound assumptions. And we can say, given this totally hypothetical scenario, what sort of difference does it make to our outcome? So, for example, if you're looking at fish habitat, if your region is going to become drier and warmer, river flows will almost certainly go down. That's relatively straightforward to model, at least sort of generally. And you can look at what changes to fish habitat will occur under that scenario. And then you can relate that back to the project. So if a project is reducing river flows by 50%, and you've done an assessment and you find out, well, there is some adverse impact, but it's not significant. All of the fish that live there will continue to live there. And now you run a climate change scenario and it dries by another 20%. And you go, oh, well, now we're seeing the river's actually going to go completely dry for 5 days a year. And we're going to strand fish. Now we have a significant adverse impact. And so these sensitivity scenarios can be really informative about sort of all sorts of environmental conditions, but they can also be done just to sort of understand our model better. So for example, if we have some inputs that are uncertain, for example, a water flow, say you're modeling the Peace River and you've got inputs from all of the tributaries except 2. You don't really know what the flow is from these 2 tributaries because nobody's measured it. You have a general idea about this watershed size, so you can make some assumptions, but you're really uncertain about whether you've done the right assumptions. So for these 2 tributaries, in this example, you've downscaled flows from 2 similar tributaries, but you're really not certain about it because you've never actually measured flow. Maybe conditions are a little different there. You can say, okay, well, what if I'm wrong? Let's do a sensitivity analysis and add 50% to those flows that we've assumed, or subtract 50%. And then you can look at your overall model and you can say, did this make a difference or not? And so that's why it's called the sensitivity. Is your system sensitive to a certain change in an input? And so with a sensitivity scenario, you have to be really careful to keep absolutely everything about your model completely fixed except for that one variable that you're going to change. Otherwise, now you don't really know whether the changes you're seeing in your output is due to one input or another. So you keep absolutely everything fixed, you change one thing, can be up or down, and then you see the output. And that really gives you insight into the model uncertainty, which is a huge thing that we need to know at the end of the day. How certain is your model? Do these changes make a difference if you're wrong? Do these changes make a difference if there's something we can't predict, like the climate in 50 years? If it's different from what we've expected, does it really change the conclusions of your assessment? And that's what it comes down to. It's not really so important, does it change this flow or that air quality concentration by 10%. What it really comes down to is, does the conclusion that I've made about this assessment in terms of yes or no to significant adverse impacts, does it change that conclusion? So at the end of the day, that's really what you want to get from your model uncertainty. So this is called a tornado plot. It's a very useful tool to show the results of a sensitivity scenario. And I've just kind of thrown in some random example. Well, not that random. This is maybe a sensitivity analysis that you may or may not want to do, but I've made up all these the data for this. But it does represent what might really be done. So say you've got a model that simulates all of the variables shown on the left: runoff, concentration, velocity, habitat suitability, temperatures, navigability, and aesthetic value. And so you need to be concerned about all of these things if you're going to alter a river in any way. And now you say, okay, well, I've done this model, I've predicted far into the future. What difference does it make to my results if I change the precipitation by a certain amount? And so what that's showing is, this is the change that we've put into the model as an input, and this is the change in the outputs. So the wider the bars means the greater the change. And so they're layered intentionally with the biggest one on top, so it looks like a tornado. And so now you can look at that and say, well, the biggest change, if there's a change in precipitation, it'll change the runoff by 11%. It'll change the concentration by 11%. And you can often color code them so that you have a positive effect on one side and a negative effect on the other side, because this is just showing the value. So for example, a higher concentration, even though it's positive, higher concentration is usually bad. So now the color coding kind of lets you know whether the change is good or bad. And the left or right just tells you whether it's positive or negative in terms of the actual value. So those are useful, really, if you're trying to communicate a model to somebody. How sensitive are these different inputs to the output? I'll also mention, it also gives you a lot of insight to where you need to be really precise with your inputs. If runoff is the big concern, then you need to be very diligent with the way you've represented precipitation. However, if you really only care about aesthetic value, it's not that sensitive to precipitation. Aesthetic value is essentially people walking along a river, looking at it and enjoying the scenery. If the river's 10% lower, does it really affect aesthetic value? Probably not. But it might have a big effect on concentrations and velocities and that sort of thing. So this helps you sort of prioritize mitigation as well, because it tells you if you make a small change in this, you will have a large change in this other variable. And often sensitivity analysis can be a lot more simple than looking at all the variables in a tornado plot. This is an example from a lake that receives mine effluent. And in this scenario, we were modeling the lake, looking at the salinity in the lake. And the salinity in the lake is largely driven by water that seeps into the underground mine. So it's an underground mine. There's miles and miles of tunnels under the ground. Water seeps in, and the groundwater is much more saline than the surface water. But when the water seeps in, it gets pumped out. Otherwise, the mine shafts fill with water, and it gets discharged to the lake. And so the question here is it going to exceed this threshold? This is the guideline that they have to meet in the lake. And so we've run two scenarios. The solid line is near field, so basically just past the point of discharge, and the dashed line is the far field, so essentially far out into the lake where everything's fully mixed. And we have two scenarios here, and the two scenarios differ in the groundwater predictions. So somebody had done a model of the groundwater trying to predict the amount of water that seeps into the mine, and they were very uncertain about how much water that would be. So for us to look at the lake now, we can't say, well, it'll be below guidelines or not. All we can say is, if the groundwater model, if this scenario that the groundwater modelers ran is correct, it'll be below guidelines. Or if this scenario they ran is correct, it'll be above guidelines. So this is definitely a what-if scenario. It's probably going to end up somewhere in between, but we can't say with any certainty because all we have is these sort of what we call bookend scenarios, a high and a low. And hopefully we've captured the high and the low properly, and it will end up being somewhere in between there. But that, again, comes down to how well the groundwater modelers have done their job. Here's another sensitivity analysis. This is looking at the Athabasca River, and the question here is, should mines treat their water and discharge it to the river, or should they stockpile their water on site, recycle it continually, and only discharge what's left over at closure? And so the drawback to stockpiling your water is that it's going to build up salts over time. The benefit is that you use less water overall, and you don't have to discharge anything during operations. But essentially we have these two scenarios. So the purple is the discharge scenario, discharging during operations. So it makes concentrations go up in the river. But the stockpiling and discharging later scenario, which is shown in green, will show higher concentrations down the road. So it's really a question of now or later, which is better, which is worse. But by running these two scenarios, we can now compare them fairly effectively against each other and make that decision, how is this going to be managed? Uncertainty is a huge topic. The sensitivity and the things we just talked about are kind of a small part of that. But there's lots of different pieces that go into uncertainty. And at least in terms of modeling and perhaps in terms of the whole EA, this is usually the part that's done most poorly by everybody because almost nobody truly understands the uncertainty of what they're predicting. But people can be fooled into thinking they understand the uncertainty. And I'll explain that in a minute. So the biggest source of uncertainty is almost certainly going to be the conceptualization. So you've done a conceptual model, you're going to base your assessment on that, you're going to base your model on that, but you've left out a key piece of that concept. So maybe it's some process that happens with chemicals, maybe it's some input to the system that you've neglected to consider. Can be lots of different things, but basically if you haven't conceptualized your system properly, almost everything that's going to follow will be wrong. And the extent to which it's wrong is difficult to determine, but usually that's where sort of the gross errors come from, is that error in conceptualization. Another type of gross error is usually like basically a typo or shifting numbers in Excel or something. And those are usually pretty easy to spot because you're going to come up with some nonsense number. But the errors in conceptualization can be really, really difficult because you can do the math 50 different ways and double check your math. But if you've conceptualized it poorly to start with, all of that double checking will tell you absolutely nothing about where your errors are. So the next are pretty obvious sources of uncertainty, but very difficult to quantify. So the quantity of input data, so do you have enough input data? Have you measured enough of your biophysical environment to actually put it into an assessment? And this applies with or without a model. But particularly when you're constructing a model, have you collected enough data? So if you're looking at groundwater, this is often a big issue in groundwater because plumes will travel through the ground and there's very limited boreholes or wells available. So plumes can travel past your wells and you've completely missed everything. Basically anything that's hard to measure and is spatially heterogeneous is going to be problematic in terms of the quantity of input data, as well as anything that's changing a lot through time. So for a spring freshet, if you've only measured twice during that month, you've almost certainly not hit the peak. You might have got the rising and falling limb, but you have no idea how high the flow actually got to that month. So you need to look at the quantity of input data, you need to graph things out, look at whether or not your observed data actually makes sense in terms of what you expect from the variable of interest. There isn't really any guidance on what exactly makes up the right quantity of input data. And so that makes it really hard to know what is the uncertainty based on this particular data set that I've got, because you don't know what the true data set is. And then the quality of input data. So the quality of input data often reflects back to the measurement methods. So you can have tons and tons and tons of data, measure every second for 2 years, but if you've been measuring incorrectly, that is completely useless and your conclusions are going to be wrong. But again, it's really difficult to know when your data quality is not good because you don't know the true value. You only know what your data set is telling you, unless you have some means of comparing to measurements somebody else has done, or you've done a lot of quality assurance around taking duplicates or replicate samples. You've measured whatever it is you're measuring many times. You get the same answer using different methods. So there are ways of controlling for that, but again, it's very difficult to know truly if your data are of good quality. So the next ones, like I said, so transcription errors, typos, any of this type of thing usually leads to a gross error, which is immediately obvious. These usually don't lead to sort of a subtle error that you're going to miss, although sometimes they do. The numerical code you're using. So if you're developing a model, are you actually using the right formulas? Does it match your conceptual model? Often, if you're modeling something, there's multiple different numerical codes you can use. And you have to basically just pick whichever one's best. They're all simplifications of some sort. And it's a matter of picking the right one. So then there's the infinite factors that can affect the future. So with developments, I talked about market failures, political will to change things, other proponents who might come along and announce a project 2 years from now. There's really no limit to the things that can affect the future, and the best you can do is make some assumptions, be very transparent about why you've made those assumptions, but that's often a big source of uncertainty that isn't really discussed very well. And there's also uncertainty about the proponent's development proceeding as planned. So the proponent will get an environmental assessment certificate if they're approved. That certificate will lay out a bunch of conditions that they have to follow, but it doesn't cover every single detail of the project. And proponents can do a lot of variations after it's approved, because they usually go through about 5 stages of engineering. And at the EA stage, they're usually in the first or second stage. So it's like pre-feasibility. They're just trying to see if this thing actually can be built. It's none of the details are worked out ever before an EA, because all of that work to actually get it to a constructible project is going to be extremely time consuming and expensive. Nobody wants to go to that level of detail until they actually have an approval in hand. So the Tech Frontier project, which was pulled a couple of weeks ago, is a great example of that. They spent $1 billion and in the end walked away. So I think they were at about the 3rd level of engineering out of 5 in that case. So they'd come a fair amount of ways, but even at $1 billion, they're still not at the point, they're not even close to where they could actually go out and build that mine. So probably would have been another several $100 million to get to that point had they been approved. And it's kind of useful to remember or to keep in mind the way that uncertainty increases. So if you're doing a simple mass balance, there's really no uncertainty around that mass balance. We know that masses are conserved. We know that energy is conserved. The uncertainty in that will just be in your inputs. If you're modeling a physical process, physical processes that use fundamental physical equations are usually pretty accurate. They're usually just based on momentum. And as long as your inputs are good, those are very reliable models. Moving down the chain, we have chemical reactions. Those are usually fairly predictable, but there's all sorts of things that can interfere with a chemical reaction. Usually they're biochemically mediated. Moving into our next category, which is biochemical reactions. So eutrophication, growth of different organisms, all of these things are based on laboratory rates, and they behave beautifully in the laboratory when they're on an agar plate. Once they're out in the environment, it doesn't go so smoothly. So you often get sort of an order of magnitude type uncertainty around these predictions, particularly if you're working in an area where concentrations are very low, and you might even have things at the detection limit. The one I missed here is actually geochemical models. These are often based on, a kilogram of sample that's ground up, taken to a lab, run through a test like a humidity cell, measure the runoff every week, try and see how concentrations are changing, and then you put that in a model, and your kilogram of material now represents 100 million kilograms of material at a waste rock pile or something, or a storage area where they're building a highway. So you're scaling up tremendously by like 7 orders of magnitude, and a small error here makes a big error once you scale it up. So that's a big challenge, but getting to the highest order of uncertainty is usually in biological models. So wildlife movement, wildlife growth, all of these things we're now modeling living creatures that can sort of behave as they wish. They don't necessarily have to behave just like your model thinks they will. All sorts of different things can interfere with that. So these models, we shouldn't be worrying too much about the exact prediction that these models are making. We just want to sort of know, is it predicting generally something better or worse, and approximately what's the magnitude. But we really have to be careful about taking the absolute values of these predictions and treating them as if these are actually what's going to happen. And then we have coupled models. Most models in an environmental impact assessment are coupled to some other model. So flow models are a really good example. In Site C, there's a flow model. Based on that, there's a water quality model, there's a temperature model, there's an ice model. All of those three latter models are entirely dependent on that hydrology model being accurate. And so, for example, in that ice model, the ice model is now a function of all the uncertainty that went into the surface water regime model, plus all the algorithms and input data that went into the ice model itself. So when we couple models, we're also coupling the uncertainty. And then I put at the bottom here, uncalibrated and unvalidated models should be viewed with caution. So a lot of times it's not even possible to calibrate a model. We might be modeling something that's going to be built in the future. So for example, a cooling pond, if there's a thermal power plant of some sort, whether it's coal or nuclear or whatever, they usually have a cooling pond. Before the project is built, that cooling pond doesn't exist. We can't calibrate our model to something that doesn't exist. We can maybe try and calibrate it to another cooling pond if we have the luxury of having another one available to us. But often it's an uncalibrated, unvalidated model. It's our best guess at what the system will look like. It's much more uncertain than if we have a model that we've actually compared to field data. So one way that we can often look at our numerical uncertainty, and this is where we can sometimes fool ourselves into thinking we know exactly what our uncertainty is, if we're not careful, is we can run a Monte Carlo simulation or a stochastic simulation. The way we're doing that, shown in this schematic here, is we have a bunch of different inputs. Each of these inputs has its own sort of set of probability distributions, or maybe it's a flow model and we have 10 different scenarios of precipitation. We have many different possible inputs for each of these. And so what we'll do is, in a stochastic simulation, the model will randomly pick from each one of these distributions, pick one value, run it through, run another simulation, pick a different value from each of those inputs, run that, and run it several hundred times, and then we have a probability bound that we can actually apply some sort of a probability to each value. The thing I was saying earlier about fooling ourselves, so this only tells us our known unknowns, so our known uncertainty. If we've conceptualized our model improperly, this does absolutely nothing for us. If our inputs are all wrong, then this does nothing for us. This really assumes that our inputs are correct. It assumes we have a good distribution, and all it can tell us is, given this known amount of variability, how much variability is there in the output. So it's a little bit like a sensitivity analysis, except we have probabilities associated with things. So this is the results of a stochastic simulation. I'm going to show these graphs again later, but for now I'm just going to talk about the outputs. And so these are time series of concentrations in a pit lake. And the dark green is the 5th to 95th percentile. And so you can look at this right away, and this is predicting copper over time. And the first thing you'll notice about this is that our uncertainty here is huge. And that's because some of our inputs have a wide range. Some seasons they're super high, they can vary by like 3 orders of magnitude. Maybe in the winter when not much is happening on site, everything's frozen, there's not much runoff, copper will be at like 1 microgram per liter. All of a sudden spring freshet comes along, it picks up a lot of material, washes into the little channels running around the mine, and now copper is 300 micrograms per liter, which is pretty close to the actual value that we used here. And so what that means is in our lake or our water treatment plant or whatever, there's a wide range of possibilities because we don't know when freshet's coming next year, how big it'll be, whether freshet will actually occur before the snow melts or whether we're going to have rain on snow. Like there's all sorts of things we don't know, and that's reflected in this uncertainty here. But then we have something like molybdenum, which doesn't vary much, even during freshet. Most of it, there's not much particulate molybdenum. So high flows can come across the site and wash it, but it doesn't really make much difference. And our inputs reflect that. We have a very low uncertainty. Same with selenium. Selenium, even though it's very high, this is 15 times higher than the limit. Even though it's very high, it's very constant. So the uncertainty bounds are super useful for us when we have a good data set that's well characterized, which we did in this case. But we still have to be careful that we keep in mind this is only telling us how much uncertainty there is in the results based on our known variability. So there's another concept in modeling which again I think is often poorly done, and so that's what I call the black swan simulations. And there's 2 relevant metaphors here. So the first one is Karl Popper's metaphor, which is the white swans. So for centuries, the white swan was used as sort of a metaphor for, you can look all you want, you're only going to find white swans. So swans are all white, that was the hypothesis, and it held until 1697 when somebody went to Australia and discovered a black swan. And so the point there was that you can keep finding more and more white swans all you want, but you're never going to actually validate or confirm that hypothesis that all swans are white. In contrast, a single observation can completely invalidate your hypothesis. So taking that to models, if your inputs are only looking at white swans, your outputs will only see white swans. So if you haven't put something in there that's unexpected, your model can't tell you anything about something like, for example, a spill. If you haven't put a spill into your model, you don't know what the results of a spill will be. Now the spill is not the best example because the white swan is the black swan is referring also to the Nassim Nicholas Taleb metaphor. He's got a book named after this, which is an event that comes as a surprise, has a major effect, and is often inappropriately rationalized after the fact with the benefit of hindsight. And so some examples of this that he uses in his book are Hurricane Katrina, which after the fact everybody said, oh, this was totally obvious, those dikes were going to fail, the levees were poorly constructed, it was only a matter of time. Everybody who looked at this said, oh, this is so obvious. Although nobody in advance really was warning about this. Same with 9/11. When the Twin Towers came down, lots of people were saying after the fact, yeah, this was bound to happen. This has been done in a couple of movies already. We should have seen this coming. But really nobody had really taken that seriously before the fact. So in the modeling world, what we need to do is we need to put some thought into, what is that black swan event? So it can be an earthquake, for example. If you have a dam, have you planned for an earthquake in the area, even if it's very unlikely? And so for Site C, they definitely did plan for earthquakes. But there's all sorts of things that under normal circumstances we would never think of, but sometime in the future they're bound to happen, and when they do, it completely invalidates everything that we've modeled, everything that we've assessed. It just renders everything useless because it's such a major event. So usually it's large geological events, landslides, wiping something out, terrorist attack, really, really weird weather like a gale storm that turns over lakes that have been meromictic or have never mixed. All sorts of things like that we should put some thought into and, if possible, run a scenario to simulate it. The reason this is an issue is because when this isn't done, inevitably lots of projects will face some sort of a scenario like this, and then people will look back and say, well, this was never assessed. But just saying, well, this was unexpected is not really a satisfactory answer to anybody. So put some thought into what that black swan might be and simulate it if possible. A lot of these things can't even be simulated, in which case it's really good just to acknowledge this is a possibility, it's remote, but if it were to happen, here's what we think it would do to the project or to the environment around the project. So Qaqc, this is a big topic. Definitely you need to spend some time doing Qaqc, not necessarily as much as what's shown here, but this is sort of a typical, on the left, this is a typical Qaqc kind of plan. This is an actual Qaqc plan that I used to work with. And so it has a lot of elements to it. We have the controls shown in green and our sort of steps along the way shown in blue. So specific work instructions, technical procedures, sort of our standard operating procedures go into our field data. That keeps the quality high by ensuring that people are actually collecting things the way they're supposed to, collecting duplicates, collecting splits, collecting in the right method, wearing gloves, not contaminating. All of that stuff is listed in these procedures. Chain of custody, that keeps track of our samples. Pretty much any type of sample that's going to be shipped off to anybody. So if you're collecting invertebrates, often those will be sent to a specialist to identify and count them. You need a chain of custody that goes with that so that the person who's going to actually do all the identification signs and takes control of that, and now they own the data until they send it back to you. With any kind of laboratory, there's usually an accreditation process. The laboratory will analyze samples, so that can be directly samples for your team or samples from, say, Environment Canada that you then use their data. Typically, if you're doing a large project like this, you'll need a really good database, and you'll need a lot of procedures around that database to make sure it's working properly. This is showing a distribution tool. There's all sorts of different tools that you might use to come up with model inputs, and at each of these steps, a really good Qaqc process is having a senior review or a peer review. So if you have teams of 5 people, you're doing a model, you should definitely have somebody else on your team go through it and be really critical and say, did you enter this input data correctly? Did you look at that? But having a separate set of eyes, preferably somebody who wasn't sitting beside you while you were doing the model, but somebody totally separate to come in and do what's called a cold eye evaluation. So they're looking at it as if they've never seen it before and giving you a good grilling and making sure that you understand exactly what's in there. Then with pretty much any model, if it's if it's a model that is developed by either the US government, which most models are, or a third party like GoldSim. There's a bunch of other companies that develop models. They should have user manuals that lay out pretty explicitly the steps you need to take and things that you can do to make sure that it's high quality. And then all of this is before you've even produced any output. So at this point, all the QA/QC has gone into the inputs, into the setup. But then once you've actually done some simulation, you'll have a bunch of output, and you need to do a thorough quality control check on that output. So do the ranges make sense? Are there things going on in your model results that you can't explain? If there's anything that you can't explain as the person who developed the model, you better go back and figure out why it's giving you those results. And the one on the right is probably too detailed. It's really specific to screening water quality data. But what I would say about this is for each one of these boxes, there will be another sort of set of flowcharts like this. So this one, this is actually the flowchart that goes along with the distribution tool. So pretty much each of these little boxes would have its own flowchart of a whole bunch of steps that you need to go through to check things off that you've properly verified your data. So I've talked a lot about models, but without really even talking about the different types of models. And so these are kind of the main types. So a deterministic model is one that produces a single result or a single set of results. So it's one very specific scenario. It tells you nothing about the uncertainty. You've plugged in one set of numbers and produced one set of results. This is often done for EAs. And again, it's difficult to look at this and say, now how certain I am about this result. Really, it's impossible to say that. Because you don't even know what the variability of your input data are because you've only run one set of numbers. So moving that up kind of one level in sophistication is a stochastic model. So you can have the exact same model that you've just run. And so I'll use the noise model as an example. You've got 5 different sources of noise. Each one of those you have a value for. You've got your receptors, you've run it through the model, you have one set of results. But if you want to make it more sophisticated, you can actually assign a distribution to that. So say blasting, the noise varies depending on how much dynamite they use, and you've got some idea about how that varies. Maybe instead of having it at 140 decibels, it can range anywhere between 100 and 180. So now you can actually run a simulation that says, you know, if we do a whole bunch of different blasting events mixed with a whole bunch of different noise from roads and from haul trucks and from whatever other noise is going on site, what is that likelihood that it will exceed a certain value? So again, another type of modeling, which you can use the exact same model setup, is a steady state model. These are usually simpler though. So a steady state model is usually actually a fairly simple calculation. All you do is you take the very worst case conditions of all of your inputs and run one simulation or one calculation that says, here's the result of that. And so, for example, if you're running a simulation of water quality, you might take the highest input concentrations, the lowest flow, and that's often the 7Q10. Lowest running 7-day flow in a 10-year period. And so all you do is you look at the highest discharge rate and you say, if that's discharged to this river on a 7Q10 period, here's the number you get. And again, it's one number, it's one scenario. Usually it's not just worst case, but often it's an impossible scenario because you don't get all those worst case conditions happening at a time. And so usually this is kind of like a first step that you would go through. If you're doing an assessment and you look at all these worst case conditions and you put them all together into one scenario, into one steady state scenario, you put all these worst case conditions together and still the effect is not all that bad, then you probably don't need to get more sophisticated than that. Because in a lot of cases, even though there's worst case conditions adding up, the consequence is fairly minor. So if that is the case, your job is actually done and you don't need to go to a more complicated model. So mechanistic model can be either deterministic or stochastic. It doesn't tell you about that type of model. Mechanistic model, all it means is that it's simulating fundamental processes. So rather than inputting flows of water, it will actually calculate the flow of water based on precipitation. So it's doing some mechanism within that model. Another one that I use a lot is a hydrodynamic model. And so that is going to tell us about how water mixes within a lake. But the way it's going to do that is by taking the shear force from wind going across the lake and translating that into momentum and using these fundamental equations to then translate it into a water movement. And so that is in contrast to the next type, which is an empirical model or a statistical model. These are based on some observation where we observe X in association with Y. And so if we were using that wind mixing model, we would say whenever the wind gets above 10 meters per second, the lake current goes above 1 meter per second. And that is only valid under the specific conditions where we measured it. And so a big problem with these models is that somebody might take a relationship like the wind mixing that's observed on Okanagan Lake and say, well, I'm going to just apply that to Duck Lake. But of course, Duck Lake doesn't behave anything like Okanagan Lake, and so our empirical model is totally invalid. That's just one example, but it's done quite a bit where somebody has observed some relationship between an input variable and an output variable and applied it to some other system where it's not really a valid application. So the thing you have to be really careful about with these models is that if you're applying it to any other system except where it was observed, that other system better be darn near close to identical to the system where it was observed. And another problem with these is that if you're taking an empirical relationship from the past and applying it to the future, you better be sure that the future actually is going to be exactly like the past in terms of all the variables you care about. So these are a little bit dicey, and I personally stay away from them. Okay, so model validation. There's some interesting commentary around this one. Really, this is an argument that goes back about 30 years about whether or not you can truly validate a model. And it also goes back to the discussion around Karl Popper's White Swans. If you have a model, in this case they're talking about a groundwater model, can you actually prove it? And these authors argue very strongly that you cannot prove it or validate it. And their point is that a model is a hypothesis. We can only invalidate it if it's wrong, but we can keep measuring all over the place within our model domain. It might be right, but that doesn't mean the whole model is absolutely correct. So the reason they wrote this paper is because in modeling, we often refer to validation as running a model, making some prediction, and then comparing that prediction to measurements that are taken in the field. And that is a very useful exercise. So if you want to model how elk will move around a dam, you can develop your model, and then after the dam is built, you go back and you measure it, and sure enough, you've measured 12 elk that behaved exactly like you thought they would. But that doesn't mean that every elk on Earth is behaving exactly as you thought. So that's their point here, is that you can't truly validate a model. And so I prefer to use the word post-audit. The reason I don't use that one a lot is because people go, what the heck does that mean? Because everybody just uses the term validation. But post-audit it does have a specific meaning, and that is taking a set of model predictions that are on the public record that cannot be altered, and then comparing them to what actually happens in the environment after a project's built. So I find that to be very useful. It's basically the proof is in the pudding. You can make all the predictions you want, but unless you actually go out and measure them, you really don't know if your model is accurate. The other thing about it is it's totally independent. So if you create a model, say of noise again, you can model the noise from the construction of Site C, and during construction, somebody can actually go out and measure that. They can go to the exact receptors where you've made your predictions, and they can monitor the sound during blasting, and they can compare that to what you've predicted, and there's no way you can go back and kind of fudge it. So unlike any sort of part of the model process, the model setup, when you're making the predictions, it's very difficult for an independent person to judge whether or not you've done everything as accurately as you can. But once you've put those results on the public record, like on the CO website, for example, where your EA will reside, somebody can take that, take your predictions, and independently verify them and see if you were right. Often your results won't be right, but then the question is, number one, does it matter? Because we wouldn't expect any model to be 100% accurate. It is a simplification. Question is, does it actually change your conclusions? Is it off by 2%, 100%, 1,000%? How far off is it? And the big question is it off in the right direction? So I talked a lot about doing conservative assessments in one of the earlier lectures. If we've done our model properly, anywhere that we're really uncertain about an input, we'll pick a very conservative input. So for example, noise again. If you don't really know whether the Hall fleet will cause 80 decibels or 90 decibels, if you're doing an environmental impact assessment, you better pick 90 decibels as your input, because if you're wrong, well, you've overpredicted the impact. You've maybe made a prediction that was a little bit too worst case, but then the risk assessment that followed from it didn't miss anything. In other words, they didn't say everything's fine, and then the blasting happens and it damages hearing or whatever, causes disturbances, and you've predicted it in the wrong direction. So you always want to be making predictions in a conservative direction wherever there's uncertainty. So that's the first question when somebody measures it and finds out you were wrong, is does it change the conclusions? But then beyond that, you want to know why it's wrong. So is it because you had something wrong with your model, which is possible, in which case you want to use that to improve your model for the next time you do it. It could be because the proponent didn't actually build the project the way they said. Back to the noise model, if blasting is 130 decibels, maybe the proponent didn't actually tell you they were planning to do 6 blasts at once, and now it's a cumulative noise that's much higher. Maybe they've kind of gone outside of what they planned to do, or just didn't give you enough information. So that's an entirely plausible scenario. There's all sorts of reasons why it can be wrong, but as an EIA practitioner, you really want to know why you were wrong so that you can improve the next time. And then the last part of that is, does the proponent now need to go back and adaptively manage? So they've predicted some effect. They've predicted that it would be below thresholds. Turns out the effect is actually above a threshold. Now they need to go and fix it. So that is a really good reason to validate models and predictions. So, as I say here, unfortunately, this rarely happens. If the regulator is wise enough to make it a condition of approval that all the models be validated, which has really only happened in the last few years, pretty much all provincial and federal regulators are now doing this, which is really good. But up until then, I had worked on hundreds of models, and the number that I'd validated or done a post-audit on is 4, which is not good. The reason I hadn't done it is because as the practitioner, you have no ability whatsoever to just go and validate your model using your client's data unless the client actually asks for it, because they control the monitoring that goes on after, they control the data. I mean, there is some ways of doing it if the data go up into a public database, but really it's not going to happen unless the proponent either is proactive and decides they want to know, or the government says you must validate this. So interestingly, one of the 4 that I did was on Peace River. So this is a post-audit. It's not after the project was developed, but this is monitoring that was completed 2 years, I think it was 2 years after the EA predictions had been made. So the lines on these graphs are what we had actually put in the EA in terms of, this is what, temperature. So we're showing think this is water temperature in dinosaur reservoir. This is where we calibrated our model. So we had predicted that on a certain day of the year, it would be something like this. Now you're predicting very specific conditions, so we don't expect it's going to be perfect. But it's pretty close. I was pretty happy with that. So we're showing generally the right layer of stratification, sort of ballpark temperatures. And then in terms of the concentrations, the lines are what the model predicted would happen during this period, and the dots are actual spot measurements that were taken on those days. So I was pretty happy with that. Another one is, again, back to Snap Lake. So Snap Lake had an EA done in, I think it was around the year 2000. It's either 1998 or 2000. Anyway, it doesn't matter. The black lines was actually what was in their environmental assessment way back then. And the blue and the orange these are the same model scenarios I showed in the sensitivity scenario. It's just a different time scale. But up until, I think it was somewhere around here, these were actually measured conditions. So now what we're doing is we're comparing the EA to today's level of knowledge. Because the mine was going for some sort of an update, and the first question the board asked, which was a very good question, is how does this compare to what you predicted 10 years ago, or are you still on track with what you said? And amazingly, it's actually pretty close. Even though it shows a fair amount of scatter here, this is pretty good comparison for an EA, where the information base is very limited. Here's another validation of the same data set. So the blue diamonds are actual measurements taken at lots of different points in the lake. So as you can see, they have a ton of data. And the lines here are the two different scenarios of model predictions. Or actually, sorry, those are two different points in the lake. So some of these models work out really well, some not so well. Again, I'm going to go back to these graphs I showed earlier, but now I'm going to focus on the data points. So this is an interesting one. These predictions were made in April of 2015, and they were under an emergency order because water was building up on site. They had a major catastrophe happen with their tailings dam, but the water had to be treated and discharged, so we did this model in a bit of a rush, hoping to come up with something fairly accurate. We weren't really sure how it would turn out. So these predictions were made before this date, and then we started monitoring afterwards, after the model had been done, and some of them turned out beautiful, like molybdenum sulfate was really good. A couple of them were very conservative, so phosphorus and copper, which is fine from an effects assessment. We don't care if we've over-predicted. Turns out phosphorus was precipitating out of solution, so we hadn't accounted for that. That was an error in conceptualization, but because it's an error in the right direction, we're totally happy with that. But the one that caused me great grief was this one here, because we had made this prediction in April, and every month I would get a new data point, and I would look at it and I go, okay, well that's a little bit off, no big deal. That's a little bit off, that's quite a bit off. And so at this point I had no idea what was going to happen after here. All I knew was that this is heading badly in the wrong direction. Turns out it was just some oxidation byproducts that had been built out and just needed to be flushed from the system. But at that point it caused quite a bit of panic. But the interesting thing was it caused a big investigation of all the materials on site, and we narrowed it down to which materials were causing this. It really helped us understand a lot of the processes going on site geochemically. So a great deal of learning actually came out of this model being wrong. So it turned out to be a really good thing. It turned out to be a great thing because it reversed itself without any intervention. This is another one we did. Muskeg River is in the oil sands area, and so these are cumulative distribution curves. So again, this is concentration, and this is the likelihood of reaching that concentration. So this doesn't tell you anything about time. What we did here is we had done predictions at around 2004, and we came back in 2008, 2009, 2010, and measured the data and compared it against those predictions. And this was a true post-audit, so The Muskeg River mine was built somewhere around the early 2000s, and they wanted to do an expansion. And so before we did that, we said, okay, let's go check the model, see if the model we used last time is correct. And at that point, the mine was operating. They were affecting the river as we sort of expected they would be. And we were actually quite amazed that the model was as good as it was. So some of the values were almost perfect. They followed the distribution really closely. And some of them we'd over-predicted. So again, at a given probability, so the median probability, 0.5, we were predicting somewhere around 0.00007, and the actual value is around 0.0004. So we're over predicting, we're fine with that. Basically things are better than what we predicted, and everybody's happy. But anyway, every time you do this, you learn a lot. If you're doing any kind of modeling and you have a client, you should tell them, plan to do this in a few years. Otherwise, you're not really making a good decision about how you're managing your risk if you don't really know if your information base is right. Model iterations and iterative refinements. So an iteration basically means a rerun of your model. And pretty much all models will need this, particularly an environmental impact assessment, and there's lots of reasons for that. So if you've done a model, a noise model, water quality model, methyl mercury model, it doesn't really matter. During the process, you'll do some sort of model, you'll produce results. Usually somebody who's a risk assessment expert will take those results and do some sort of a risk assessment on it. We will talk about risk assessment in a week or two. But usually it's not the modeler who's interpreting these things. And often you've been very conservative in your inputs. You've sort of looked at worst case scenarios. You've chosen inputs that are on the high side so that you minimize your chance of underestimating effects. And as a consequence, you've way overestimated the effects. And then the risk assessment person looks at this and says, okay, everything within 100 miles of here is going to die if this project gets built. And you go, well, hang on. That might actually be partly due to the conservative assumptions in my model. So now you go back and look at them and you go, how realistic were these inputs? And so that's probably the number one reason that we need to do iterations, is to refine the model to make it more realistic so that we're not overestimating effects, which do nothing except scare the crap out of people unnecessarily and make a whole bunch of expensive mitigation necessary. So that's one big reason. Another reason, which sometimes happens, is we've done a baseline study. It took us 2 years. We're now sitting down, we're doing our assessment, and this part definitely applies to the assessment in general, not just the model. But somebody's gone out and collected a couple of years worth of data. Now we've been doing our assessment for the better part of a year, and the person who's been collecting the data sends us a data set which is totally different, and something happened in the environment that wasn't expected. Can be virtually anything, but it now changes our conceptual model. We think a little bit differently about what's going on in the baseline conditions, and that has big implications for our assessment. So now we need to go back and do an iteration. Another one, so I'm not going in order very well here. I started with level of conservatism. So another one is that the scenarios change. So the proponent now, let's say BC Hydro, has been having you do an EIA for a couple of years. You've done the baseline, you're halfway through your assessment, and BC Hydro now has a new rate forecast because the economics have changed a little bit, and they say, well, we were going to do 1,100 megawatts. We've changed our minds. We're going to do 2,000 megawatts. Can you please update all your models? So that happens fairly frequently. Mitigation may need to be updated. So using fish as an example, you're doing a fish assessment, you're looking at some of the tributaries to the Peace River, and you realize that there are going to be some significant adverse impacts to fish. And so your assessment reflects that, and you take that to the client, in this case BC Hydro, and you say, look, if you build this dam in this way, you are going to have significant adverse impacts, which is bad for everybody. It's including bad for you because you're probably not going to get approved. So what can we do about it? Can we divert a stream? Can we add some habitat elsewhere? Can we compensate? Either way, almost certainly there will be several iterations like this where you'll add mitigation, it will reduce the effects, you maybe add some treatment to a water treatment plant, add tertiary treatment or something. It can be virtually any type of mitigation. Once you've added it, now it's going to lessen the effect of the project and you can redo your assessment. Another one, which is a little more technical, is having dynamically linked models. So a good example of this might be an ice model. So usually there's very specialized teams doing each model. Somebody does a surface water regime model, and it predicts the flows in the Peace River. Then somebody who is an ice specialist will do an ice model to try and understand how the ice jams work. And they come back to the surface water modelers and say, well, you just modeled your river with no ice. These are the flows you got. I've now put an ice module on top of that, and lo and behold, it's actually going to cause an ice jam, which is going to completely change your river model. So now you need to do an iteration that includes the feedback from that linked model. So iterative refinement, it can be very time consuming. Depending on what it is, sometimes it's fairly quick and you can just insert something into your model and rerun it, but sometimes you're going all the way back, altering your conceptual model. If you alter your conceptual model, you can alter virtually anything about your assessment. So sometimes can lead to a big amount of redo. Now, what I wrote at the bottom here is that they're almost never reported. So the model and the assessment, iterative refinements, we don't normally report those because it would be basically another 25,000 pages or so. Often these EIAs will be stacks and stacks of binders, and if we now had to go and write it all about the iterations that went into it, we would have more stacks and stacks of binders. So it's partly practical. It's also partly that we don't do a full report until we're actually done with the model we're happy with. So in other words, we don't come to the point where we're predicting significant adverse impacts, write a big report, and then go back and change our model. We wait until everybody's sort of satisfied that all the mitigation that can be applied is applied, all of the refinements that have gone into the model and to the assessment have been put in there, and now we write the report. And all of those things that went into that are typically not tracked. And so as I said here, it leads to the perception that a model is a rubber stamp. And the reason people say that is because they see this final report and lo and behold, there's no significant adverse impacts on this massive project. And they say, well, you just did this assessment to show there's no adverse impacts, but actually part of the process is identifying the impacts, mitigating the impacts, iteratively updating this and coming up with a project that's actually suitable. It's not a matter of just assessing it for the sake of trying to make sure there's no adverse impacts. A huge part of it is actually improving the project. And so if they only see the final product, they don't realize that the initial project might have actually been quite bad for the environment until the EIA started, and through that process it became a much, much less harmful project. So I'm not sure what the solution to that is. Possibly some of those iterations could be reported, but keep in mind if you're doing one that you're probably going to be doing lots of iterations. Okay, so I haven't talked about linked models yet. I'm not going to talk a ton about this. It's just good to be aware that there are lots of models that are linked together. This gets pretty technical. So I just mentioned a river model and an ice model. There's also a river model and a geomorphology model. There's a river model and a water quality model. There's lots of different models. Groundwater model links into the river model. There's lots of different things where one team completes a model, their output goes to another team, whose output goes to another team, and it gets pretty complicated in terms of actually trying to get all these models to talk to each other. Here's a few examples. This is from an EIA I did back in about 2012. It's called the Qaqc mine, and this is showing how 9 different models are linked together. So in this case we had 3 different operational periods, so what I referred to as snapshots last week. So during the construction and dewatering period, we have dewatering of one lake into another lake. We have, so that's number 1. I can't remember why the order goes in this way, but so in lake number 3, we now have an affected lake being discharged to another lake. And then linkage number 4 is actually a fish habitat model looking at any effects of fish from these changes in flows. And then during operations, this is showing the water management pond. So we have one model that's looking at the circulation of water, trying to understand whether sediments will be stirred up. That's number 5. And number 2 is a geochemical model, taking very, very small samples to the lab, grinding them up, running through humidity cells, and using that information to understand the chemistry coming out of the process plant going into that lake. And then at closure, we've got a whole lot going on. So the mine's being reclaimed. There's number 8 there is showing seepage from a tailings pond into the lake. Number 2 is the basic water chemistry of the lake itself. 6 and 7, so 7 is tailings that are put in a pit, which are consolidating and releasing water. 6 is showing the circulation in the lake. Anyway, you don't have to remember any of those details. Just the point is that in an EIA, often there's lots and lots of models linked together, and it's a real challenge to make them actually speak the same language, because generally all different models have different file types, they run on different time steps, they run on different domains, and you have to make it sort of comparable so that the results make sense at the end. This is a similar one. This is the Qatc mine. Again, similar types of things. There's a project that has a discharge to a lake. In this case, all the models are shown in different colors. So there's a dispersion model to understand the near field effects, hydrodynamic model to understand the large lake effects, and a regional water balance model showing all the different tributaries coming in to understand how much flow comes into this lake. Now, this is very specific to water quality models, so don't worry too much about the details. But with most types of models, you need to understand what's called the dimensionality. So I've shown them separated here into 0D, 1D, 2D, and 3D models. So a 0D model has no dimensionality. It's basically just some calculation of some process without any real spatial dimension to it. 1D model, a river model is usually a 1D model, so it changes as water moves downstream. A 2D model is applicable to something like a wide river, where you've got dispersion coming across and water moving downstream, but vertically it's well mixed, so you don't care about that third vertical dimension. Another example is lakes. Lakes are often 2 dimensions, except with lakes they're laterally averaged, so there's no gradient from left to right, but there is from upstream to downstream, and there is from top to bottom, because that's basically how lakes work. And then you have 3D models, which are usually not necessary, and they're usually really slow to run, really data intensive, and very difficult to use. So one thing that is relevant is if you look at the arrows on the right, where it shows the 3 main considerations. So ease of use, without the dimensions, the model is usually pretty easy. Yeah, if you're just basically using a model as a calculator, it's a lot less data intensive. You don't have to put in the geometry of the system you're using. This applies to any type of model, biological models. If you have to make it spatially aware, your computer has got a lot more processing to do. You've got a lot more input data. And so that second arrow shows computational demands as you move in dimensions. But then ability to simulate complex interactions, that's the third arrow, so that goes, that increases with your dimensionality. So those are important considerations, and this concludes our discussion of models.